In 10 hours, a telescope in the mountains of Chile found more than 2,000 objects in our own solar system that no human being had ever seen before. Not distant galaxies, not far-off nebulae, rocks, asteroids, moving through the same solar system you live in, some of them close enough to Earth's orbit to matter, and every single one of them had been sitting there undetected for the entire history of human civilization until a machine the size of a small car turned on for the first time and simply looked. 7 of those 2,000 objects were near-Earth asteroids, meaning their orbits bring them close enough to us that astronomers track them specifically because of what they could do if their paths ever crossed with ours. And this was not a specialized mission built to hunt for dangerous space rocks. This was a general-purpose survey telescope doing basic calibration tests, glancing at the sky almost incidentally, and stumbling into more previously unknown near-Earth objects in a single night than most dedicated asteroid hunting programs find in weeks. If a telescope can do that by accident during its first 10 hours of operation, the real question isn't what it found. It's what has been out there all along, that nothing on Earth was watching for, until now. This is the real story of what the Vera C. Rubin Observatory's first images actually revealed, and why the most experienced astronomers studying near-Earth objects are calling this the beginning of a genuinely new era in planetary defense. I'm your host, and this is your channel. If this is the kind of story you come here for, subscribe now, because we're just getting started. To understand why the Vera Rubin Observatory's very first images sent a ripple through the planetary defense community, you first have to understand what kind of machine we're actually talking about, because nothing quite like it has ever existed before. It sits on the summit of Cerro Pachon in Chile, one of the driest, darkest, most astronomically stable locations on Earth, and it's built around an 8.4-meter primary mirror paired with the largest digital camera ever constructed, a device roughly the size of a small car, capable of capturing 3.2 billion pixels in a single exposure. A single Rubin image covers an area of sky equivalent to 45 full moons. To put that in perspective, the Hubble Space Telescope, for all its extraordinary detail, sees roughly 1% of the moon's surface area in a single frame. Rubin sees 45 entire moons worth of sky at once, in exquisite detail, and it does this over and over, scanning the entire visible southern sky roughly every 3 to 4 nights, for the next 10 years straight. It is not built to zoom in on one object. It is built to watch everything, all at once, continuously, and notice what changes. That distinction, watching for change, rather than taking a single static picture, is the entire reason this observatory matters so much for planetary defense specifically. Most objects in the night sky, stars, distant galaxies, don't move in any way you'd notice from one night to the next, but asteroids do. They drift across the background of fixed stars as they orbit the sun, and the only way to reliably find them is to photograph the same patch of sky repeatedly and look for the faint points of light that shift position between exposures. Historically, this has been a genuinely difficult trade-off for astronomers to manage. You could use a telescope with a narrow field of view that's sensitive enough to catch faint, distant asteroids, but it only covers a tiny sliver of sky at a time, meaning most of the sky simply never gets checked with that level of sensitivity. Or you could use a wide-field telescope that covers much more sky, but typically at lower sensitivity, meaning it only catches asteroids that happen to be unusually bright. Jonathan Blazek, an astrophysicist at Northeastern University who studies Rubin's data, put it simply, when you finally combine one of the largest telescopes ever built with the largest digital camera ever built, working together, you get both advantages at once, wide coverage and high sensitivity, and that combination is exactly what you need to find asteroids that aren't huge, which is exactly why Rubin found so many so quickly. On June 23, 2025, the National Science Foundation and Department of Energy released Rubin's first test imagery to the public, and the numbers behind that early data are the real story here. In just over 10 hours of test observations, spread across only a handful of nights during the observatory's commissioning phase, Rubin identified 2,104 asteroids that had never been cataloged before anywhere in the world, including 7 near-Earth asteroids. NASA and independent astronomers confirmed that none of those 7 posed any danger to our planet. But the number that should actually give you pause isn't the 7, it's the 2,104, because that number came from a telescope that wasn't even trying yet. It was still in its testing and calibration phase, essentially getting warmed up. Mario Juric, an astronomer at the University of Washington who has spent years preparing for exactly this moment, described the early results plainly. Finding more than 2,000 previously hidden asteroids in just a few hours of observation wasn't even difficult for Rubin. The asteroids, in his words, simply popped out of the data. Now consider what that means once the telescope stops testing and starts actually working. Rubin officially began its primary 10-year mission, called the Legacy Survey of Space and Time, later in 2025, and the projections for what it will find once it's running at full capacity, are staggering compared to everything that came before it. Ground and space-based observatories combined have historically discovered roughly 20,000 asteroids per year across the entire world. Using every telescope, humanity has pointed at the sky for this purpose. Rubin alone is expected to discover well over 1 million new asteroids within its first 2 years of full operation, more than doubling the total number of known asteroids in our solar system almost immediately. Over its full 10-year survey, current projections put the final tally at roughly 3.7 million asteroids in the main belt between Mars and Jupiter, 32,000 icy objects. Beyond Neptune, and 89,000 near-Earth asteroids specifically, the exact category of object that matters most for planetary defense, because those are the ones whose orbits bring them close enough to Earth to actually pose a risk. Here is the number that puts all of this in real perspective. As of Rubin's first light in 2025, scientists estimated they had already found and cataloged roughly 70% of near-Earth asteroids larger than 1 kilometer wide, a truly civilization-threatening size class, through decades of dedicated survey work by other observatories. But when it comes to smaller near-Earth objects, the ones in the range of 140 meters wide, roughly the length of a football field and a half, and still large enough to devastate a city or region on impact, our detection rate has historically been far lower. Rubin is projected to nearly double the number of known near-Earth objects in that specific dangerous size range, pushing our overall detection rate for city-threatening asteroids up toward roughly 70% of what's estimated to actually be out there, which means, put plainly, that before Rubin came online, humanity had likely identified less than half of the asteroids large enough to level a city that are currently orbiting somewhere in our solar system's neighborhood. Blazek addressed exactly this scenario directly, referencing the kind of airburst event that occurred over Chelyabinsk, Russia, in 2013, when a relatively small, previously undetected asteroid exploded in the atmosphere with the force of hundreds of kilotons of TNT, injuring over 1,000 people from shattered glass and shockwaves alone. If something like that happened today, over a populated area, he explained, you would want advance warning, either to evacuate people or to potentially deploy asteroid deflection technology that space agencies have already begun testing. Rubin, he said plainly, is what gives us that warning. And Rubin isn't just finding more asteroids, it's revealing things about the ones it finds that older, slower survey methods could never have detected at all. In January 2026, astronomers led by Sarah Greenstreet, who heads Rubin Observatory's Near-Earth Objects and Interstellar Objects Working Group, published the first peer-reviewed scientific paper built entirely from Rubin's camera data, using observations collected over roughly 10 hours across just 7 nights during the observatory's early commissioning phase in the spring of 2025. The team identified 19 asteroids rotating at extraordinary speeds, including one designated 2025 MN45 that turned out to be the fastest spinning asteroid larger than 500 meters wide ever recorded by humanity. This object, roughly 710 meters across, wider than most skyscrapers are tall, completes a full rotation in just under 2 minutes. To put that in perspective, most asteroids of similar size take hours, sometimes many hours, to complete a single rotation. This one spins fast enough that the centrifugal force at its equator is pushing right up against the edge of what should be physically possible for a loosely bound pile of rubble to hold together without flying apart entirely. Scientists believe extreme spin rates like this are usually the result of a violent past collision with another asteroid, meaning objects like 2025 MN45 aren't just newly discovered, they're carrying physical evidence of ancient impacts written directly into their rotation. Evidence that simply couldn't be measured before a telescope existed with the speed and sensitivity to catch it. What makes this discovery particularly significant is where most of these fast-spinning asteroids were found. Nearly all of the newly identified fast rotators live in the main asteroid belt between Mars and Jupiter, rather than closer to Earth, where most previously known fast-spinning asteroids have been detected. That's not because fast rotators are rarer out in the belt. It's because objects that far away are much fainter and harder to see. And until Rubin came online, no telescope had the combination of light-gathering power and precision needed to catch them at that distance. Regina Remeka, the Department of Energy's Associate Director for High Energy Physics, described this specific discovery as direct proof that the observatory's core technology is already pushing the boundaries of what astronomers believed was observable at all, delivering results within Rubin's very first uncalibrated test run that would have been considered ambitious goals for a mature, fully operational survey. This pattern, discoveries emerging faster and in greater volume than anyone expected, has continued well beyond the asteroid detections. By the spring of 2026, using data gathered during Rubin's early optimization surveys, astronomers had cataloged 380 new trans-Neptunian objects, icy bodies orbiting far beyond Neptune in the frozen outer reaches of our solar system, adding meaningfully. to the roughly 5,000 such objects discovered by all other astronomers combined over the past 3 decades. 2 of these newly found objects, provisionally designated 2025 LS2 and 2025 MX348, have such large, elongated, stretched-out orbits that at their most distant point, they travel roughly 1,000 times farther from the Sun than Earth does, placing them among the 30 most distant minor planets ever identified in our solar system. And by May 2026, less than a year after Rubin's first light, the observatory's growing catalog had reached 11,000 newly discovered asteroids overall, alongside confirmation of 80,000 previously known ones, and 33 additional new near-Earth objects, with the largest of that batch measuring roughly 500 meters across, again, confirmed to pose no current threat, but every single one of them a previously invisible object, now permanently on humanity's radar. None of this means there's a specific known asteroid on a collision course with Earth. There isn't. Every near-Earth object Rubin has found and analyzed so far has been confirmed as safe. But that's not really the point, and it's not the reason planetary defense scientists have reacted to this observatory the way they have. The point is what these first few months revealed about the size of the gap in our knowledge that existed before Rubin turned on. For the entire history of human civilization, we have been sharing our solar system with tens of thousands of city-threatening asteroids that no one had ever seen, tracked, or measured, simply because the technology to find them at this scale and speed didn't exist yet. Rubin didn't create that population of objects. It simply revealed, in its very first 10 hours of operation, how much of it had been sitting there in the dark the entire time, completely unmonitored. Mario Jurich, reflecting on just how quickly the discoveries came, said the asteroids essentially found themselves, popping straight out of the very first dataset the telescope produced. That is the actual headline buried inside Rubin's first images. Not a single dramatic threat. A quiet, overwhelming confirmation that our solar system's inventory of nearby hazards has been, this entire time, only partially known, and that the tools capable of finally completing that inventory only just switched on for the very first time in 2025. Rubin's full 10-year legacy. Survey of space and time is only just getting underway, and every additional night of observation adds to a real-time, continuously updating map of exactly what is orbiting near us. Information that space agencies around the world are already treating as a foundational input for planetary defense planning, deflection mission design, and early warning systems that, until now, were working with an incomplete picture. The telescope that produced 10 million galaxies and 2,000 new asteroids in its very first test run is only going to get more sensitive, more comprehensive, and more thorough as its survey continues, and every single object it finds is one more piece of our solar system's neighborhood that used to be invisible and now, for the first time in human history, isn't. If this kind of story is what you come here for, one that shows you what the universe is actually revealing, instead of exaggerating what it hasn't, hit subscribe and turn on notifications, because we're going deeper into what Rubin finds next time. Drop a comment telling me what surprised you most about how much has been hiding in plain sight, and share this with someone who needs to see just how much of our own solar system we're only now starting to actually map.